Hello everyone, this is the video for lecture 19. Today we are going to finish chapter 14, after which we move on to chapter 22. So we've talked a lot about waves so far, but we haven't really talked about the importance of a wave. And that's what the first bullet point tells us. A traveling wave transfers energy from one point to another without transferring the medium itself. To make sense of that, imagine that you and a friend are each holding different ends of a rope. If your friend flicks one of the ends of the rope, they'll send a wave that travels down the rope and eventually gets to you. Okay, when that rope gets to you, or when that wave gets to you, your arm is going to jerk up and then it'll come back down. So what happens is that wave is energy that's being transferred to your arm, right? And that energy is what's causing your arm to go up and back down. However, none of the actual rope, or no more of the rope than you're already holding, is transferred to you. You still have that little piece of rope you're holding. The wave transferred energy to you, and it did not transfer any extra rope to you. So the energy has moved from one point to another, but the medium itself hasn't transferred very much at all. So far, when we've been talking about waves, we've mostly been talking about one-dimensional mediums, such as a rope or a string. We also saw a video where a rock was dropped in a pond, and then waves spread out in 2 dimensions along the surface of that pond. Hopefully you can extrapolate from this into 3 dimensions. In the picture on the right, you have a source at the center, and this source is creating waves in 3 dimensions. The waves are spreading out all around that source, so they're spreading out equally in all directions, and this is creating these, what we call spherical wave fronts. And that is what's shown by the black lines around the source. If I were to draw this in 1 dimension, or if I were to superimpose a 1-dimensional wave onto this, I would put the crests of the wave at the spherical wave fronts. So it would look something like that. Okay, so now this leads us to the intensity of a wave. We define this as how much energy is transferred onto an area over some time interval. The formula for intensity is I equals delta E over area times time, delta T. So delta E is the amount of energy that's transferred. A is the area that energy is being transferred to, and delta T is the time. This is actually equal to P over A, where P is power and A is area. So for that last equality, recall that power is rate of energy transfer. So it's the amount of energy that's being transferred in a certain amount of time. So P is equal to delta E over delta T, and then A is just area. So notice that intensity has units of watts per meter squared, and that's because power is measured in watts and area is measured in square meters. And to understand why we are using area here instead of length or volume, again, let me draw your attention to the picture on the right. These black wave fronts are meant to represent spheres. And if I just look at the surface of the sphere, or if I just look at part of the surface of the sphere, then that surface is going to be 2-dimensional. And in 2 dimensions, we have to talk about area. I can also just draw a sphere like this, I suppose, and imagine that sphere to be 3-dimensional. If I just look at a patch of surface area of that sphere, it's going to look something like this. And that patch has an area. So that's where the area comes from in the intensity formula. the source is transferring energy in the form of these spherical wave fronts. And if I'm looking at, in particular, a small patch on the surface of one of those spheres, then that source is delivering energy to that area. Now, intensity is indeed related to what we hear when we hear a sound or a sound wave. However, it's a relatively inconvenient scale, and we prefer this decibel scale. So we say the perceived loudness of a sound that we hear is measured using the intensity level beta, where this fancy B is the Greek letter beta. So beta is defined as 10 decibels times the log base 10 of the intensity divided by this I0. Beta is also called the decibel level. If you're familiar with sound, you may have heard this term before. The units for beta are decibels. And decibels are sort of interesting as a unit. Well, first they were named after Alexander Graham Bell for his work with the telephone. But they're also one of the sort of natural units that rely on this prefix deci. So let me remind you of the prefixes real quick. You have kilo, hecto, deca. Then you have the base unit. And then after the base unit, you have deci. Deci is rarely used, but decibels is one example where it's quite common. This I0 is a reference level for intensity. It is called the threshold of hearing, and this is the lowest intensity that human ears can naturally detect. So I0 is equal to 1 times 10 to the minus 12 watts per square meter. And of course, everyone's hearing differs. So this is sort of an average of the lowest intensity that humans can hear. Now let me pull you back up to this equation, because it's strange that we have 10 decibels there. It's strange that we have a number with a unit in the equation like this. We do this because logarithms do not have units. Inside of the logarithm, we have intensity in the numerator, and we have an intensity in the denominator as well. Those two intensities cancel each other out, so there are no units in this log at all. So then that 10 decibels in front is what's defining the units for beta. Logarithms, by the way, if you remember from math class, this is a function. It's the inverse to the exponentiation function, the e to the power of x, or I guess in this case 10 to the power of x. The log base 10 refers to this 10, and the other common logarithm is the natural log, which is the inverse for the e to the power of x function. For our purposes, you don't have to know too much about logarithms. Mostly what you have to know is that there is a button on your calculator that says log. There may be two buttons, in fact, one that says natural log or ln, and one that is log for log base 10. Now, just by using math, we can show that if the intensity of a sound is increased by a factor of 10, then the intensity level increases by 10 decibels, by an additive 10 decibels. So if I multiplies by a factor of 10, then beta will increase by plus 10 decibels. So also I have here as a rule of thumb, if a sound increases by 10 decibels, then humans typically perceive this sound to be about twice as loud. So hearing is, it's very much based in human perception, and oftentimes it's hard to capture this in a mathematical equation, but this is the rule of thumb we use. Every time a sound goes up by 10 decibels, you're going to hear it as roughly twice as loud. And so this is the correspondence we use here. I times 10 corresponds to beta plus 10, corresponds to loudness times 2. Okay, so at the bottom I ask, what is the lowest decibel level that human ears can detect? I0 is defined as the threshold for human hearing, the lowest intensity that human ears can detect. But what's the lowest intensity level or decibel level? Think about it for a second and unpause when you're ready. Well, to calculate the lowest decibel level, we use the formula for decibels. You have beta is equal to 10 decibels times the log base 10 of the intensity divided by the reference level. In this case, the intensity is the reference level, so we do I0 over I0. If you simplify a little bit, you get 10 decibels times the log base 10 of 1. And again, if you remember from math class, the log of 1 is equal to 0. So this is going to be equal to 0. You can also plug that into your calculator. It should also give you 0. So then the lowest decibel level that human ears can detect is 0 decibels. This is not a coincidence, as you can imagine. The decibel level is based on human hearing. So it starts at the lowest that humans can hear. And just to be clear before I move on about calculators, well, every calculator is different, but on many calculators you will find a button that says ln. This is the inverse function for that e to the power of x I was talking about. On most calculators you will also find a button that says log or log base 10. These buttons are usually have the same thing, and your calculator will have one or the other, but these are the inverse function for 10 to the power of x. Okay. So now question. Demonstrate that multiplying intensity by a factor of 10 increases the intensity level by 10 decibels. So I want you to show that correspondence I had on the previous page. And I want you to try by starting with the threshold of human hearing. And so increase that intensity level, I0, by a factor of 10, and show me that the decibels, beta, increases by plus 10. Try it out and unpause when you're ready. So you can do this on your calculator. If you start with the threshold for human hearing and you increase by a factor of 10, then you use the formula for beta to calculate this, 10 decibels log base 10 of 10 I0 over I0. The I0s cancel out, one in the numerator, one in the denominator. And then you have the log base 10 of 10. Since the log base 10 is the inverse of 10 to the power of x, log base 10 of 10 actually just gives you 1. And you can check that on your calculator. So then you're going to end up with beta is equal to 10 decibels. So if the threshold for hearing, I0, gives you 0 decibels, 10 times that gives you 10 decibels. Your next step would be to check 10 times that. So 10 times 10 I0. This would give you 100 I0. And if you go through the steps, you'll end up with log base 10 of 100. Here you're going to get 2 instead of 1. And then you'll have 2 times 10 decibels is 20 decibels. And you can keep going on. Every time you multiply I by 10, you'll be adding 10 to beta. This, of course, is a few examples of how to do it, but as you can imagine, I would like to keep this mathematical. So let me show you a more mathematical proof of this. The first thing I have to do is remind you about a property of logarithms. So if you have the log of two things that are multiplied together, so the log of two numbers a times b, then you can write that as log of a plus the log of b. So basically, if you multiply them together inside of the logarithm, you can sort of add them together outside of the logarithm. Okay, so that's the property we need to use. Now I want to start with an intensity I, and I want to increase that intensity by a factor of 10. So then I'm going to start with beta is equal to 10 decibels times the log base 10 of I over I0. That will be our beta 0, or let's call it beta 1 to make it a little less confusing. Then I'm going to multiply that I by 10 and compare with beta 1. So beta 2 will be 10 decibels times the log base 10 of 10I over I0. I'm going to rewrite the inside of that logarithm just to make it a little more clear. I'm going to write it as 10 times I over I0. Then this 10 I want to use as my capital A, and this I over I0 I want to use as capital B. Okay, so then I'm going to have beta 2 is equal to 10 decibels, and then in big parentheses I'm going to write the log based 10 of 10 plus the log base 10 of I over I0. Okay, the log base 10 of 10 is going to be 1, just like it was before, and again, you can check this on your calculator. And then I want to distribute that 10 decibels over the parentheses, so I'm going to get 10 decibels times that 1, so I'm not going to write that, plus 10 decibels times log base 10 of I over I0. Okay, that second term is just beta, or beta 1 in this case. So what I end up with is that beta 2 is equal to 10 decibels plus beta 1. Okay, and that demonstrates what the question is asking. If you multiply the intensity by a factor of 10, then the intensity level increases by plus 10 decibels. On the right here, I have a table that gives you some standard values for intensity level. Starting at the bottom, you have the threshold of hearing. This is at 0 decibels. At 10 decibels, you have a quiet rustling of leaves. That's a typical intensity level for that. If you whisper very quietly, this will be at roughly 30 decibels. Normal conversation occurs at 50 decibels. If you go a little bit higher, you see that there's this thing called the threshold of pain. At about 120 decibels, sounds will start to actually cause your ears to hurt. This is why sirens in rock concerts are at 120 decibels. For rock concerts, of course, they want to play the music as loud as possible, so they play it right at or below the threshold of pain. And the same would be true for sirens, right? They want you to hear the sound, but they don't want to cause you pain. Note that the threshold of pain is, it's not the same as when sound can start to damage your ears. As I'm sure you've heard, if you listen to loud music over a long period of time, then that can damage your hearing. And you usually will not listen to music at the threshold of pain. So actually listening to music below 120 decibels for a prolonged period of time will cause damage to your ears. So here's another question. An ambulance siren is initially 100 meters away, and the intensity level you hear is 50 decibels. So let's draw this out. You have an ambulance that is blaring noise, and that ambulance is 100 meters away from you. Okay, and when you hear that noise, you hear it at 50 decibels, an intensity level of 50 decibels. When that ambulance gets to be 10 meters away from you, the question is asking, what is the intensity level that you hear? This is actually a hard problem at this point, so let me give you a little hint. The area for the surface of a sphere is given by 4 pi r squared. And r, in this case, is the distance from the center of the sphere. Okay, so it is a hard one, but think about it for a minute or two and unpause when you're ready. So the ambulance is blaring its siren in 3 dimensions, and it's emitting these sound waves in all directions, which we can represent as the spherical wavefronts. From the center where the siren is located, the wavefront would be located at a distance r. Okay, so that's what r is going to represent in this equation. Okay, so now notice that the siren is initially at 100 meters, and when it's closer to you, it's 10 meters away. So the siren actually has moved 10 times closer to you, or this distance r has decreased by a factor of 1 over 10. It started as 100, and it went to 1 over 10 times 100, which is just 10. Okay, so when r decreases by a factor of 10, what happens to beta? That's essentially what the question boils down to. So let's see, r decreases by a factor of 10. We can actually relate r to intensity because we know intensity is power over area, which is going to be power over 4 pi r squared. So now if r decreases by a factor of 1 over 10, the intensity, well, we have to calculate what the intensity will change by. So then we can write r goes to 1 over 10r implies that I goes to p divided by 4 pi 1 over 10 r squared. And then I just want to simplify this a little bit and compare it to the original. The 1 over 10 r squared is going to become 1 over 100 when you square that 10. And then you have 1 over 100 in the denominator of a fraction. So you want to pull that out front by flipping over that 1 over 100. So you're going to end up with 100 times p over 4 pi r squared. Okay, so then this is 100 times what we initially started with, the initial intensity p over 4 pi r squared. So if r decreases by 1 over 10, I will increase by a factor of 100. Okay, so that almost gets us there. The question's actually asking about beta. So if I increases by a factor of 100, notice that this is the same as I increasing by a factor of 10 twice. So then if I increases by 2 factors of 10, beta is going to increase by plus 10 decibels twice. Right? Each time you multiply I by a factor of 10, you increase beta by plus 10 decibels. Okay, so then you're going to end up with beta is equal to, or I'm sorry, beta increases by 20 decibels. Okay, and that's going to give us the answer. When the ambulance gets 10 times closer, beta will increase by 20 decibels. And if beta starts at 50 decibels, the answer is going to be 50 plus 20 is 70 decibels. And then a quick follow-up question. How many times louder is the siren when it's only 10 meters away compared to the initial 100? So that rule of thumb we're using is that every time beta increases by 10 decibels, the sound sounds twice as loud. Here, beta is increasing by 10 decibels twice, so then you're going to increase the loudness of the sound by two times. Okay, hopefully that's clear, but the short of it is that beta plus 20 decibels is the same thing as beta plus 10 decibels plus 10 decibels, which is going to end up with a loudness times 4. So the ambulance will sound 4 times louder when it has moved to 10 meters away from you. Most of the info on this slide we've gone over on previous slides, so I'll leave the first couple bullet points for you to go over, as well as the picture. But let me bring you to the bottom bullet point. We have this relationship for spherical waves that the intensity is equal to the power divided by 4 pi r squared. Okay, so then this tells us that for spherical waves, I is proportional to 1 over r squared. In physics, we call this an inverse square law, and we actually see it quite often in physics. Two cases that come to mind that we've seen in our physics class is for the force of gravity, the universal, Newton's universal law of gravitation, where you have capital G times the two masses divided by r squared. Here you have that the force of gravity is proportional to 1 over r squared, so that's an inverse square law. And then the second one that we've seen is for electricity. You have E is equal to K times Q over r squared. This was for a point charge, the electric field for a point charge. So you have that the electric field for a point charge is proportional to 1 over the distance squared from that point charge. So again, you have an inverse square law. And I suppose also related to the electricity, you have the Coulomb force, the force of electricity, is when you have two charges, but it basically looks the same, proportional to 1 over r squared. Let's take a closer look at these wave fronts at the bottom. We start with a source that's emitting waves in all directions. Those waves we are representing by these wave fronts. The wave fronts which we depict as the crest of the waves, these are a distance lambda apart. They are a wavelength apart. As we go from the left picture to the middle picture, we are just getting further and further away from that source. So as the wave fronts get further and further away, they start to look like this in the middle. And notice that as I'm getting further and further away, this section just to the right is starting to flatten out. When I'm very close to the source, this region looks relatively curved. As I get further away, that region becomes flatter and flatter. If I get much, much further away, that region that I'm highlighting might as well just be a flat line. Okay, now here I'm talking about pictures in 2 dimensions, but if these pictures were to represent spheres in 3 dimensions, then the region I'm highlighting would be an area rather than a flat line. That area is what's shown in the right picture as what we call these wave fronts, or plane wave fronts. Right, those regions that I was highlighting before start to look like flat planes. Okay, so then when you get far away from the spherical waves, those small portions look flattened out, and we approximate these with what are called parallel planes or plane waves. Okay, this question is similar to the ambulance question, which was a hard question, but now that you know how to perfectly answer that one, hopefully you can work through this one. So I will let you read through it, think about it for a minute, and then unpause when you are ready. Okay, you can basically work through this in the same way that we did the ambulance question, but here I'll do it with a different method, just to expose you to different techniques. So we'll work with ratios this time. What we're going to calculate is the intensity at the far point divided by the intensity at the close point. Okay, so you have a train that starts 40 meters away from you. So the intensity far is going to be P divided by 4 pi, and then you have 40 squared. Right, that train's emitting sound as waves in all directions, and that sound is coming out of the train as these spherical wave fronts. So we'll use this equation for intensity. And then for I close, we will use the same equation, but with 20 meters. And then I want to plug that in at the top. I'm going to, let's see, the p's and the 4 pi's are going to cancel with both. So I'm not even going to write them. For I far, I'm going to have 1 over 40 meters squared. And for I close, I'm going to have 1 over 20 meters squared. So I can just simplify that a bit. I will get 20 meters squared over 40 meters squared, where the square is, of course, on the number and the unit. I will end up with, well, at this point you could just plug it into your calculator, but I will keep working with the equations. So in the numerator, I'm going to have 20m all squared In the denominator, I'm going to write this as 2 times 20m all squared. The 20 squared is going to cancel with the 20 squared in the denominator, and I'm going to be left with 1 over 2 squared in the denominator, or just the 2 squared in the denominator. So I'm going to end up with 1 over 4 total. Okay, so I have the intensity at the far point at 40 meters divided by the intensity at 20 meters is equal to 1 over 4. Okay, I can just rearrange that to make that look a little nicer. I will get that the intensity at 20 meters is 4 times the intensity at 40 meters. Okay, so that means the answer is going to be E. Right? The question is asking, what is the intensity of the sound waves from the train's horn when it is 20 meters away from you? And the intensity will have increased by a factor of 4. Okay, so here's a less mathematical question for you. As you know, you can break a wine glass with your voice. For instance, okay, that video is funny, but also kind of annoying in many ways, so I'm not going to play through it, but it's there for you if you want to watch it. So then, knowing that intensity tells us how much energy a wave transmits, because I is equal to power divided by area, does the wine glass in this case break because of the intensity of the wave, or of your voice? So that is the sound wave coming from you transmitting enough energy to the glass to cause it to break? So actually, in this case, it's not because of the energy from the wave, or from the intensity of the wave. The wine glass actually breaks due to resonance, right? That boy's voice was loud, but it wasn't that loud, not loud enough to break the glass. And it was this resonance, which is something we will talk about in a few slides, that actually causes the wine glass to break. Now that said, it is possible, generally speaking, to break glass with intensity, but you need a very, very intense sound. Here's an example I found on YouTube of a sound with a huge intensity. So you have this meteor entering the video at the top part of the video. This meteor is entering the atmosphere, and as it enters the atmosphere, it explodes with this huge boom. Okay, so you're going to hear the video quiet for a few seconds, and then you're going to hear this huge boom as the sound reaches the camera. You'll also hear glass nearby shattering. Okay, that was the Chelyabinsk meteor. It happened a few years ago. And so let me say I'm not an atmospheric sound expert. And I couldn't really find much of a discussion of this on any online physics forums or anything. But in my opinion, this was likely due to a shock wave coming from the meteor. When combined with that huge intensity of the wave, it was enough to cause all of that glass to break. So let's talk a little more about this resonance. Let me remind you from last lecture, or a few lectures ago, that we learned about damped oscillators, where you have this oscillation, this back and forth motion, that is decreasing over time. The amplitude of the oscillation is decreasing because of friction. And eventually, that oscillation would stop. Right? Once the amplitude goes to 0, the oscillation stops. One way we can counteract the damping force is with an external force, and this is called a forced vibration. So as an example, if you have a child swinging back and forth, if they stop pushing themselves on that swing, eventually they're going to come to rest at the bottom of that swing. in order to keep the child going, we can push them periodically. Okay, so we're sort of, we are the external force, and we're forcing the oscillation, the back and forth motion of the swing. And this is counteracting the damping force that comes from the friction in the chain. This external force that can reinforce the oscillation, sometimes we call it a driving force. And there's a few different ways that a driving force can affect an oscillation. For this class, we are only interested in one case, and that's what's described on this slide. So imagine you're pushing a child. All right, you push them, they swing away from you, they go out as far as they're going to go, and then they start to swing back. Right? They swing all the way back, and then as they're moving away again, you push them again. Okay, then they swing out, they swing back, start to swing forward, and you push. Out, back, push. Out, back, push. So your pushes, right, the driving force for this swinging motion, occur at the same point of the motion every time. So the frequency with which you are pushing is matching the frequency of the swing. Now we say in general, when the frequency of the driving force equals the frequency of the oscillation, we say that the system is in resonance. And as with the case of the swing, resonance can cause an increase in the amplitude of oscillation, which can oppose that damping or the friction in the chain. The dotted line in the graph at the bottom might represent the swing going back and forth with friction, right? If you're not driving that motion, it's eventually going to come to rest. However, if you push the child every time they start to move away from you, then the dark blue line will represent the motion, where you continuously increase the amplitude of oscillation by continuing to push the swing. Now we're going to see in our lab coming up that you have this driving force from a tuning fork, and the oscillation that you hear is the sound wave coming from the tube. Okay, so when you watch the lab video, you'll find that when these things match up, the sound is going to get louder, right? They reinforce each other, so they're in resonance. Now, when you push a child on a swing, you push them so that they go the same height with every swing, or maybe you try to make them go just a little bit higher, but you never go too much higher. Okay, so at the bottom, you have the dotted line that represents the child, and then the blue line represents you pushing the child. Okay, and so then they go to the same height every time. So then in the case of the child, you're basically canceling out friction, right, with your driving force. However, if the driving force is strong enough, it can actually more than make up for that friction, or more than cancel out for that friction. And in this case, the amplitude of oscillation can actually grow wildly out of control. So if instead of just giving the child a little push as they go back and forth, if you give them a big shove, the first time you shove them, they'll go a bit further. And then when you shove them again, they're going to go even further than that. Shove them again, they'll keep going further. And I mean, if they're on a swing, eventually that swing is going to flip over and the child is going to fall off. That's not so bad in the case of a child, but it can also result in something that we call catastrophic failure, or catastrophic structural failure. And here I have a few different cases of that, the first being the wine glass. Now I've muted this video because the only sound you hear is just a tone playing in the background, and it's quite a loud tone. So I've just muted it to keep that out of the way. But what we see here is a wine glass. To the left of the wine glass there's a speaker, and that speaker is playing a large tone. So let's push this forward a little bit. Okay, so you have a close-up of the wine glass here, and the speaker in this case is on the right side. The sound coming through this hole in the board is hitting the wine glass in this top right side here. As the sound hits the wine glass, you're going to see the wine glass vibrate back and forth. Okay, so the wine glass is vibrating back and forth. Okay, and there's another view of it. So as the sound waves come in, say from the right side, when they hit the wine glass, it causes the wine glass to go left. So the right side of it to go left. Every time one of those peaks hit the wine glass, it causes the wine glass to go to the left. If those peaks line up at a precise frequency, essentially the wine glass, okay, so the wine glass is going left and right. You want that peak to hit the wine glass every time that wine glass is on the right side. Right? That's going to then be in resonance with the wine glass, and it's going to cause it to oscillate more and more and more. Eventually, because the wine glass is structurally weak, eventually this sound is going to overpower the structure of the wine glass, and there it causes it to shatter. So in this case, the sound, you can play the video with sound. It's the sound itself is not that loud, but the fact that the sound wave is hitting it at just the right points, this is causing resonance. So it's the resonance that's actually breaking the wine glass. Another famous example related to this catastrophic structural failure happened at the Tacoma Narrows Bridge in Washington. And this was all the way back in 1940. So let me first apologize because the original link I have in the slides was broken, but this link here is, it goes to the actual video that I intended for it to go to. Okay, so let's check out the video. Now this video I haven't muted because it has this brilliant music and narration in the background that I love. It's just this old-timey kind of movie feel to it. So let's play it.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear.
Okay, so you have, it starts as just a normal bridge, of course. What's happening is there's wind sweeping in through this valley, and the wind is gusting at a certain frequency. Right? So each gust hits this bridge, and it causes the bridge to wobble just a little bit. Okay, but when the next gust hits at just the right moment, it causes it to wobble a little bit more. And then when the next gust comes in and it hits at just the right moment, it causes it to wobble more. So this wobbling builds up over time, and it's causing this huge swaying or twisting back and forth of the bridge. Okay, let's go back to the video.
In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center...
Okay, so I'm going to fast forward through the video, but it's there for you if you want to watch the full thing. It shows the chords up close. More and more twisting. I love this guy is just casually walking off the bridge.
He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? And cables snap like puny threads. There it goes!
And there you go. Eventually the wobbling just becomes too much for the bridge to take, and it just collapses. Now I do want to point out that there's not necessarily consensus in the community about what actually caused the Tacoma Narrows Bridge failure, and it may not be resonance itself. But still, it's a good example of this catastrophic structural failure that can occur from oscillation. And also the video is just too good to pass up. So you're no doubt familiar with this, but I do want to play this video of a car honking as it's passing by a cameraman. Okay, so you notice that when it approaches, it has this high-pitched sound, and then as it moves away, that sound becomes lower, and it has this meow sound. This is caused by the Doppler effect. What's happening is pictured in the top right. If you have a car that's just sitting still, then the honks from that car are emitting in every direction equally. Okay, but when the car is moving, so when the car is moving to the right, you have the sound waves or the wave fronts bunching up in the front of the car, and then they're sort of spread out in the back of the car. Okay, so in the front, you have the peaks, the crests of the wave are reaching you more frequently, and then in the back of the car as it's moving away, those peaks are reaching you less frequently. Okay, so when those sounds get to you more frequently, the sound is higher pitched. Pitch is related to frequency. When the sound waves are more spread out, that pitch is lower. And you can also see this in action in the animated GIF in the lower right. Once the car starts moving, the waves in front bunch up and the waves in back spread out. This effect doesn't only occur in sound waves. It can happen for any waves, basically. In the picture to the right that I pulled from the book, you have a source of the waves at the center, and that source is moving to the right. You can see the waves to the right of this source are bunched up, and the waves to the left are more spread out. We'll also learn in one of the later chapters about light waves that light can actually take the form of a wave, and light waves can also experience the Doppler effect. To calculate how those waves change in frequency, we have this formula shown in the middle of the page. First, let's look in the lower right. You have an observer that's riding a bicycle to the right. You have a source, in this case, that's sitting still, and that source is emitting sound. So then FO would be the frequency of the sound that the observer hears. Fs is the actual frequency that's being emitted by the source. V is the speed of sound in air. VO is the speed of the observer. So in this case, the bicyclist is moving with a velocity of VO. Vs is the speed of the source. So in this case, Vs would just be 0 because as pictured, the source is not moving. But when you're considering the Doppler effect, you have to consider not only the speed of the source, but also the speed of the observer. In that video with the car, you have the observer standing still and the car driving past. But it could also work in reverse. If you have a car just parked and honking its horn, and you drive by in your own car, you'll also hear the Doppler effect. Since we're talking about this relative motion between the source and the observer, we need to define some sort of standard for the signs of the speeds. Basically, we can't just say right is positive and left is negative, because we're not talking about this absolute left and right motion. We're talking more specifically about the relative motion between the two. I will let you read through the cases in the middle, but the bullet point at the very bottom basically sums it up. If one of the source or the observer is moving toward the other, then we say that speed is positive. If instead they are moving away from the other, that means we use a negative sign for that speed. And the Doppler effect has a lot of uses in everyday life. Police radar guns use the Doppler effect to determine the speed of vehicles. Basically, the gun sends out a wave. The wave bounces off of your car, and then the frequency of that wave shifts based on how fast your car is going. So when the wave returns to the gun, it can determine your speed based on how bunched up the waves are. You may have heard about this Doppler radar on news. The local meteorologists use this. The idea is basically the same as the radar guns. They send waves out into the atmosphere. Those waves bounce off of clouds, and then you can determine the speed of the clouds based on the reflected wave. And then this last one is kind of interesting as well. So as I mentioned, light can take the form of a wave, and light can experience the Doppler effect. So when you're studying galaxies that are very far away, you have next to no information on these galaxies. The only thing you can do is see the light that they're shining toward you. Now, we expect these galaxies to emit light with a certain frequency, or in a certain range of frequencies. But what we actually see is that the light is at a lower frequency than we expect. So we say it's redshifted. And this name will make more sense when we study the electromagnetic spectrum in future chapters. But basically what this means is that the galaxies are moving away from us. Right? The frequency is lower, the frequency of the light is lower than we expect, so the waves are more spread out than we expect them to be. This tells us actually that the galaxy is moving away from us. And this is true for all galaxies. If you point your telescope to pretty much any galaxy in the sky, you'll find that the light from that galaxy is redshifted. Okay, so in fact, when you look at galaxies that are even further away, that light is even more redshifted than the galaxies that are closer away. This tells you that the galaxies that are further away from you are moving faster than the galaxies that are closer to you. Okay, so then the further you go out, the faster the galaxies are moving, and they're all moving away from you. This is one piece of evidence that supports this Big Bang theory, that the universe started in a small contained area and sort of had this huge explosion where everything spread out. Okay, this slide I put in the lecture because it does show up in chapter 14. However, we're not going to use this information in chapter 14. And if we do need it when we get to the further chapters, I'll come back to it. But for now, I'm going to skip this slide. Basically, what it is telling you is how two different sources can either create waves that constructively interfere with each other or destructively interfere with each other. And so the equations and most of the info on this slide I do want to skip for now. And similarly, I'm going to skip this slide. Both of these slides will be more relevant when we start talking about diffraction of light and diffraction gratings. But this was kind of interesting. Somebody asked me last semester if you could cancel out the waves of a tsunami with another set of waves. And my answer was that it was possible in theory, but difficult in practice. But again, we'll come back to this in the future. Section 1411 talks about beats. And these are the same beats that you hear in some music, that sort of thump, thump, thump sound that some songs have. So for two overlapping waves that have different wavelengths and frequencies, the resulting sound wave that you get from the interference of the two overlapping waves can alternate between constructive and destructive interference. In the picture at the top, you have two waves. You have a yellow wave, or an orangish kind of wave, and a pink wave that starts overlapped with the yellow wave. But the wavelength of the pink wave is a little bit longer than the orange wave. So as you go further down this line, the pink wave overlaps less and less with the yellow wave until you get to the middle, and they're completely anti-overlapping. So in the middle, they're 180 degrees out of phase with each other. Then as you continue further and further, they start to match up, and they match up again by the time it gets to the ear. In the blue at the bottom, or I guess in the middle here, it shows what the resulting wave is from the interference of the two waves at the top. So since they start off overlapping, you have large amplitude constructive interference. As they overlap less and less, the amplitude of the resultant wave gets smaller and smaller. Eventually, when they're 180 degrees out of phase with each other, they cancel each other out completely. Okay, and there's no sound in the middle. Then they become more and more in phase with each other until they start overlapping again, and you have this large wave constructive interference. At the bottom, I added this GIF that shows something similar. The picture is showing these waves both traveling to the right towards this ear. So you get, in the middle picture, you have this large amplitude that reaches the ear. But then as this wave travels to the right, that amplitude decreases until it's gone. Then the larger amplitude reaches the ear, and that's where the thump, thump, thump sound comes from. In the bottom picture, you have the red wave that's not moving at all, and then the green wave is decreasing in wavelength. Okay, but the effect is fairly similar. You still have these large amplitude constructive interference areas and the small amplitude destructive interference areas. You can determine the beat frequency, or how often you hear those thumps, by taking the difference in the frequencies of the two waves. Okay, so the beat frequency is the number of times the amplitude changes in a given time interval. How often you hear those beats. You have the high and then the low, high, low. So the beat frequency equals, it's just the difference between the frequencies of the two waves, but you don't really care which wave is the first wave or the second wave, so you take the absolute value of it. And this is something you can actually hear in action. At the bottom, I have a link to a tone generator. So what I'm going to do is actually open up 2 pages, or 2 of the tone generators, and I'm going to play them at slightly different frequencies. So let's hear it first at 440 Hertz. Okay, that was one tone at 440 Hertz. Now I'm going to bump this one up to 441, while I'm going to keep this one at 440. Okay, so I'm going to play them both together now. Okay, so you heard this sort of thumping, and that thumping was occurring once per second. To figure that out, to calculate the beat frequency, we would take 440 Hertz for the first wave, and you would take 441 Hertz for the second wave. So you would do 440 minus 441. That is going to give you the absolute value of -1. So you get a beat frequency of just 1 Hertz. Okay, so that tells you that you hear that beat once per second at 1 Hertz. Right? Hertz is, again, per second. So now I'll play it again, and you can pay attention to see that you hear that beat once per second. And also what I'm going to do is play it so that the second wave is at 442 hertz. Okay, and if I do the second wave at 442 hertz, I will get a beat frequency of 2 hertz. So then I'm going to hear, in the second case, I'm going to hear 2 beats per second. So again, the first tone will be played at 440 hertz. The second one now I'm going to play at 441. And you were hopefully hearing 1 beat per second. When I bump the frequency of the second wave up to 442, you should hear now 2 beats per second when I play both. Okay, so when the difference between the two frequencies is 2, you are hearing 2 beats per second. If I bumped this up to 443, the difference would then be 3, so you'd hear 3 beats per second. 444 gives you 4 beats per second, etc., etc. So here's a question. You have 2 sound waves. The first one has a frequency of 1000 hertz, and the second one has a frequency of 1050 hertz. The question is, how many beats do you hear in 5 seconds? I want the total number of beats that you hear in 5 seconds. So think about that and unpause when you're ready. Okay, to start off, you want to calculate the beat frequency. So in this case, you're taking the absolute value of 1000 hertz and you're subtracting 1050 hertz. This gives you the absolute value of minus 50 hertz. So the beat frequency itself is 50 hertz. When the beat frequency is 50 hertz, that means you hear 50 beats per second. So every second you hear 50 beats, then over the course of 5 seconds, you're going to hear 5 times 50 beats, which is going to give you 250 beats. So the answer here is C. This question is just a wave-related question that we probably should have had in a previous lecture, but since I didn't put it in, I'm going to put it in now. So you have a wave on a string that's traveling to the right. You have this blue wave, and the blue wave is moving to the right. Immediately after this image is taken, so you take a snapshot of this wave as it's passing by, immediately after that picture is taken, I would like to know, what is the motion of that black dot on the string? Imagine this black dot is a ribbon tied to the string. I want to know, in which direction does it move immediately after the picture is taken? Think about it and unpause when you're ready. Okay, the instant after this picture is taken, the wave will have traveled just a little bit to the right. So the wave will look like this. Now the wave travels to the right, but the individual pieces of the string do not actually move left or right. Okay, the wave itself, or the string itself, only oscillates up and down. So if I'm looking at this ribbon right here in the middle, that ribbon has to stay along this dotted line. Okay, it cannot move left or right. So an instant after this picture is taken, the only place this ribbon can go is up. So immediately after this image is taken, the motion of the string at the black dot is up, and the answer is A. And this question also could have gone in a previous lecture, but it's a good refresher in any case. So you start with a speaker in a room, and that speaker plays a 400 Hertz sound wave. You then increase the air temperature in the room. What does this do to the wavelength of the sound wave? Unpause when you're ready. Okay, when we were learning about sound, we had one equation that was related to air temperature. That equation said that the speed of sound in air was 331 meters per second times the square root of the air temperature divided by 273 Kelvin. The question is asking about wavelength, but we can relate wavelength to wave speed with another equation. We know that V is equal to lambda times F. Okay, so when the temperature increases, then the first equation tells us that the velocity of the wave will also increase. Right? Temperature is in the numerator, so if temperature increases, then the velocity will also increase. Let me also remind you before I continue that this T in this equation is for temperature. When we're talking about waves, we also have this T for tension. I've been trying to distinguish it as tau, but just a reminder, this T is for temperature. Okay, so now in any case, you have temperature increases. This causes the speed of the wave to increase. And then looking at the second equation, if the speed of the wave increases, so the left side of the equation increases, the right side of the equation also has to increase. Now, since the speaker is emitting a wave with a constant frequency, F is not increasing at all. F is constant. This means the wavelength of the wave also has to increase. So temperature increases implies wave speed increases implies wavelength increases. So the answer for this question is A. And then finally, I'm going to leave you with this example, example 11 from chapter 14. So you have a piano that is supposed to vibrate, one of the strings is supposed to vibrate at 440 Hertz. So you have someone that's tuning this piano. They strike a tuning fork that always vibrates at 440 Hertz. And when you compare the sound of the tuning fork to the sound of the piano, you can hear a beat frequency. If they're not at the same frequency, you'll hear a beat frequency. In this case, you hear a beat frequency of 4 beats per second. Okay, so you have that FB is 4 Hertz. One of the frequencies is 440 Hertz, the frequency of the tuning fork. So you would have that F1, say, is 440 Hertz. F2 in this case can take on two possible values. F2 would be the frequency of the piano string, and it can have two possible values in this case. I'm going to leave that to you to figure out, and the answer is in the book. It is on page 509 and 510 in the book, but I would like you to think about it before you just look up the answer. And then parts B and C are both related to this Doppler effect. So for parts B and C, you have to apply the Doppler equation. That I'm going to let you try as well, and you can, again, look up the example to see how you're doing. And if you're confused, of course, we can go over it. This is perfectly fine. but I will leave this example for you to think about on your own. So that's going to conclude today's lecture, and also that concludes chapter 14, at least as far as the lectures are concerned. As I mentioned, after today we're going to move on to chapter 22, which is on reflection and refraction of light. So that's all I have for you. Have a good day.